us in the Cup of Tech, the first episode of it. My name is Haitham, and as Steve said, I'm a consultant and trainer for Nobel Prog. I'm specialized in data science using Python and R. I train people on Python and R. And I also am specialized in developing algorithms for supply chain. So we can talk about retail and managing the stocks of retail or optimizing the prices with regards to the assortment of the shops and these kind of things. So I develop algorithms for this key area. And I work with machine learning most of the time because I need to develop these algorithms to be in line with the history. And I can't wait to show you just a brief introduction about machine learning. And please feel free to ask me any questions while we go on the way. And if the time allows, we will also have a simple demo using Orange software for 5 minutes, just to show you how easy and simple it is to create a machine learning environment. Maybe at the end, before the Q&A, if the time allows. And I hope you enjoy this session. So what is machine learning? Machine learning is a technique where we train a computer on a historical data. It's basically a prediction or a forecasting. When we forecast for the future, we train the data from the history on some features. So for example, if I want to predict some sales, I train the data on the price. Maybe it has an effect on sales. I train the data on the weekend or the weekday. Maybe it has an effect on sales. I train the data on the location where I'm selling. Maybe it has an effect on sales, right? So these are called features in machine learning, or X, X1, X2, X3, X4, and Y is the sales that we are trying to predict. And we can use the normal statistical methods such as linear regression or logistic regression, or we can use more updated models that came recently in the past 10 or 15 years, such as support vector machines and deep learning and the versions of deep learning and these kind of things. So all of this lies under the umbrella of machine learning. You are basically training the system, your computer or your software, on historical data. And we can take the data from many places. We can take it from our database, from the SQL or the ERP system. We can take it from our sensors. We can take it from our cameras. We can take it from our geolocation sensors and these kind of things. So data can be taken from anywhere, and the structure of the data will be the same. So if I take an image, it has to be converted to numbers and rows and columns. If I take a video, it has to be converted to numbers, rows and columns, because the models don't understand images. They understand numbers. They understand characters. They don't understand images. We have to convert. So there is some conversion and cleaning to enable to model. So as we said, each of the features are X1, X2, X3, and we use them to predict Y. And this is a simple journey of supervised machine learning. We have the data. We split it. Usually we split the train to 80% and the test to 20%. However, if you have a small sample, then you might want to make 70-30 or something like this. Depends on the sample that you have, or maybe 90-10 if the sample is very small and you want the model to gain some information by training more data. So maybe 90-10. But the standard, what people use is usually 80-20 or 70-30. So we split the data into half, or 70-30. And it has to be random, because we don't want to create biasness in our model. So I randomize the data before I model it. So I remove the biasness from the training. Because, for example, I can say the features of Haitham, excuse me, the features of Haitham is arranged in an order in the beginning of the data set. And the features of Steve is arranged at the end of the data set. So if I train the model only on Haitham, the model will be biased on Haitham features. We did not see Steve's or Ayman's features, right? We have to randomize our data before we model. And then we make the model on the training data, whether it's decision tree, random forest, any the many models that we have, depends on the context, of course. And then we test the trained model on the unseen data, the one we kept, the 30% we have kept. We test the model on it and we see if the model is performing well on the test data or no. If it's performing well, we are good to go. If it's not performing well, then we might tune the parameters a little bit, change the parameters, change the threshold, change the penalty parameters, all of these, so we can have a better model, a more robust and flexible model. If everything is in good order, then we can deploy the model into production, and we can use it to predict customers' purchases, to predict whether the customer will buy or no, to predict whether a customer will default in his credit card or no. So we can deploy, we can put it into production. So this is the machine learning side. As it is very simple, and we will try to do one demo of it at the end. Please feel free to stop me if you have any questions. So we have two types. This one was supervised. Why this one was supervised? Because we know our label. We know if the person was Haitham or Steve or Ayman or any other participant. So, and we know his features. This is the training history. That's why we call it supervised environment. We have everything observed in front of us. And the supervised have two types. Have a regression type and have a classification type. So the regression type is modeling the continuous numbers from negative infinity to positive infinity. I can have from negative 200,000 to positive 1 million, continuous. And we can think about sales, we can think about speed, we can think about weight, we can think about gas concentration. All of these are continuous numbers, right? So we use regression for this kind of data, or when the label is, the Y is continuous. And for the binary data, 0 or 1 or true or false, we use classification. So we have, for example, the logistic regression is very famous for classification. If a person will default in his credit card or no, this is a binary problem. True, he will default. False, he will not default. It can be further extended to include multi-nomial. So it can have 4, 5, 6 choices, not only 1 or 2. It can be ordered as well. So it can be primary, secondary, and preparatory, secondary, university, master's, postgrad, and so on. So it can be ordered categorical variables, or it can be different categorical variables, or it can be binary, true or false. All of this lies under the classification section. So this is the supervised part. The unsupervised part, we don't know why. We don't know the target. We are simply trying to get some similarities out of our data. When you go to Google, for example, and you write how to, you find a list of suggestions. And if you complete a little bit, how to make a cake, and then you have how to make a cake with raspberry, how to make a cake with, and how to make a cake with, right? These are all suggestions because these are all in one cluster of making a cake. So when you write how to make a cake, Google puts all of the observations that were in the same cluster as how to make a cake. So this is a clustering problem. We don't know why. We just know the similarities. And based on these similarities, we cluster every observation in a cluster, in a certain group by themselves. And it is very widely used. It is used in marketing. We make clusters for customers based on their purchasing behavior, based on their frequency of buying, based on their purchasing volume, based on their loyalty. So we can put the customers into clusters by this. Many other applications as well. So in unsupervised, we find similarities in observations and we group them into clusters. Example, grouping articles by topics. This is one very good example. Or grouping customers by recency, frequency, and monetary value. This is called RFM analysis, and it is one of the most widely used applications in marketing, and it used Kmeans or the clustering algorithm to cluster the customers, and then accordingly target the customers with the suitable and convenient promotions. Also for fraud and anomaly detection. So we have some customers that are depositing in the bank very frequently with healthy amounts, and some customers, for example, shifting between banks and depositing very small amounts. So we can group and then we can see what's happening here, something is fishy or no, and things like this. So the important thing to note here, clustering, we don't know why. We are trying to get the similarities. So let's have a couple of demos. Excuse me. Okay, so this is the unsupervised one. And this is a simple K-means problem. Let's do it again. So we have these scattered observations, as we can see. Okay, so the first question in the K-means is how many centroids you need. 1 cluster, 2 clusters, 3 clusters. Let's make it 3 clusters. So as I added 1 cluster, all of those observations belong to this cluster. 2 clusters, then the observations are split between those 2 clusters. And if you notice, these points belong to the red cluster because they are near to the red cluster than the blue cluster. And for those guys, they are near to the blue cluster than the red cluster. Let's add one more. And now we have 3 clusters. So what will happen? Every cluster will center itself among its tribe, let's say. So this blue cluster will be a little bit here, and this red cluster will be a little bit here, and this green cluster will be a little bit here. So they center themselves. And then when they center themselves, you can see that belonging of some red clusters have changed their loyalty. They went to the blue cluster, right? So we have to update the centroids. And then since we updated those guys were centered themselves again. And then some members changed their loyalty. And so on, and so on, and so on, and so on, until we reach a point where the cluster has converged and there is no further changing the loyalty or changing the membership in the clusters. So those are our 3 segments, or our 3 customer segments, based on their features and observations. Very widely used, and we will do it, I think, in the training program next week, I think, in Python. And this is the one. So let's continue. Let's look at supervised learning. So what we see now is unsupervised learning. So we have here an example, a very simple example, and this is the first example I used when I learned about data science and machine learning, but it still holds till now. We have two areas, San Francisco and New York, and we have here the height in San Francisco, and we have here the height in New York. So this is the elevation in feet, or the height. And we can see here that there is some cutoff value between the heights of the apartments in New York. This is New York, the blue one, and San Francisco is the green one. First, I can, and just the first inference, I can say whatever is more than 239 feet is definitely a San Francisco home. Whatever is below 239 feet, well, we have to see about that. But now I have made my first cutoff. I have made my first if then. I have made my first rule that whatever is more than 239 feet is a San Francisco home. Now we are making a relation or a cross comparison. And you can see here, this is the height and still holds. Whatever is more than 239.5 is a San Francisco home. And we can have some more information now. Whatever is higher in square foot per price per square foot, whatever price per square foot is higher than, I think, $1,780, most probably it will be a New York apartment or a New York home. So now I have further dissected my data to gain more information about the difference between New York and San Francisco. And those are the boundaries. So I have now two if-thens. If the home is higher than 239 feet, most probably it's San Francisco home, lies in San Francisco. And if the home is more than 1,700 and 760, is most probably a New York house. And now I have two if-thens. And by the way, this is a classification problem because we have two options here, not many, not from negative infinity to positive infinity. And then we draw many conclusions from the data, like the year built and the bathrooms, the number of bathrooms in the homes, the price of the house, the square foot, the price per square foot. All of these features can tell us whether the data is, whether the house is in New York or the house is in San Francisco. So we will train this data on a decision tree, and the decision tree is doing exactly what we have done now. If then rules. If the height is more than this, then it's probably this. If the price is more than this, then it is probably this. So, and the first fork in the decision tree is the most obvious fork, which I think is the height. So you can see this is the first cutoff of the tree, or the first level of the tree. It is segregating between 47 New York homes, 47 San Francisco homes, because they are, the elevation of them is very high, and the model, the decision tree is telling me those homes are San Francisco. Let's look at the other homes. So always the split point at the beginning is the most obvious split point. So, and we see here, picking a split point has trade-off. Our initial split, 73 meters incorrectly, classifies some San Francisco home as New York ones. So, as you can see, the second we already dissected, or we already characterized or predicted the 47 San Francisco homes. But we have to further go down with the tree, or prune, or make another splits in the tree to dissect or to segregate the unsegregated feature homes. So you have to make another split to further segregate the data. And then we can have something like a tree that after it's segregated based on elevation, we are left here with some New York homes as well. So it was not a pure segregation. So we have to further segregate on the right side and on the left side. And so on, and so on, and so on. So looking at the price per square foot. And then after you look at the price per square foot, look at the year built. And then look at the price per square foot again. If then. until you reach pure observations. All pure. However, the training accuracy is 100% because I modeled the data to the lowest point. I went to the roots of the tree. So the training of the data is 100%. But when you test the data on unseen observations, the reality will be a bit different. So because I have trained the data so much on the observations it has, the model created became very rigid to what you have seen. It's not very flexible now. And most probably in the future, you will see more flexible data, not as before. So you don't want to fall in this trap of having 100% accuracy in the training and then in the testing, having a very low accuracy. So this was a simple demonstration about machine learning, the supervised classification. Machine learning identifies pattern using statistical learning and computers by unearthing boundaries in data sets. Decision tree, this is what we have done, and overfitting is not a good thing. And that begs the question of model quality. So what is model quality? To measure the model quality, we have two KPIs we need to consider: the bias of the model and the variance of the model. What is the bias of the model? If I leave features out of my training, so for example, in the decision tree, I left the year built entirely. It's not there when I was training my model. So this means that the model is a bit because he will not differentiate or he will not gain information from the year built feature. I created some bias in my model, right? So bias quantifies the lack of ability of a model to capture the underlying trend in the data, while variance quantifies the difference or the model sensitivity to small changes in the underlying data set. In simple words, the variance is the difference between what the training data set said and what the test data set said. Because the training, I have 100% accuracy, while in the test I had 89 accuracy. So there is a bit of variance here. The model is not very flexible. It's very rigid to what you have seen in the training. So you want to balance between both. We don't want to make the model very rigid, and we don't want, so less bias. We don't want to make the model, we want to make the model less bias and less variance. We want to balance between both. And you can see that there is a trade-off. Whenever this increase, this decrease. Whenever this decrease, this increase. Ideally, we want low bias and low variance, but there is a trade-off between the two quantities. More complex model decrease bias, but tend to increase variance, such as what we have seen now in the decision tree classification, because it was a very complex. The tree length was very long. And this is what we see here, that this is the variance, and this is the bias. So if we train the model up till here, we will have low bias and very high variance. And this is underfitting the model, and this is overfitting the model. So here the model is just a straight line. So these observations are under evaluated and these observations are over evaluated. The model is almost similar to random chance, almost, not entirely, but almost similar to random chance. I'm not doing any gaining of information here too much. While here, this leaves nothing to random chance. It's taking everything, right? Which is not good as well, because when this model sees the future data, it will not be like this. It will have some variability. It will have some outliers, anomalies. So we cannot also overfit like this. And we can see here at a certain point, we have the least variance and moderate bias. But then when we tend to overfit, the variance increase. Are there any questions so far? No, I think no, right? Okay. Okay, so now for the people who are entering the data science space and they want to explore more, I just want to show you an overview of what we have. We have Python as the #1 coding program, followed by R in data science, and followed by SQL. Python is #1 in coding because Python is a multi-criteria coding language. You can do web scripting, you can do web development, you can do applications, you can do data science. And most of the community who was working in web design and applications, when they shifted to data science, for sure they used Python because they already know Python. While R is more focused on data science and statistical learning and statistical language. And that's why the community of R is a bit smaller than the community of Python. However, you will find them both neck to neck, and you'll find that the community, whenever the community is developing something here, it is developing the same thing on the other side. And SQL is very popular for sure, and because this is where data lives, most of the data scientists would like to know about SQL as well, because they need to get the data from the databases. And to get the data, they have to know SQL. So my advice, if you are just starting, pick one from Python or R, and then followed by SQL. If you want to enter into data engineering world, TensorFlow is for artificial intelligence, and it is also compatible with Python and R. If you want to enter in the data engineering world and pipelines and creating applications, AWS and I think and Hadoop for big data are good languages to know. So how can we use machine learning in several fields? For example, as I said, in supply chain, I get the data from the database, and then I make calculations on the stocks that I have, and I calculate the safety stock, I calculate the minimum order quantity, and then I send this calculations to the database again, where the purchasing guys can see what to buy and what not to buy, what to get away, what to write off from the products, what not to write off. I also take the data from the transactions of the customers to gain information about the price, the sensitivity of the price. And then I create models to see what if I change the price a little bit, what will happen? They're called dynamic pricing. And then I give the actions also to the revenue managers to change the price accordingly to maximize their profit or the revenue, for example. And we have for sure the blockchain technologies and the tracking and these kind of things in the supply chain field. In the marketing field, as we said, that the people use it for the RFM analysis, recency, frequency, and monetary value. They use Kmeans. They also use churn analysis, where they try to predict if the customer will leave or will not be loyal to us anymore or no. So we can, excuse me, so we can offer him targeted promotions and these kind of things before he leaves. In finance, we all hear now about the robo algorithms that we have that can tell us what stocks to buy and what stocks to sell. And these quant algorithms that we have, if you go to eToro or if you go to IQ options, they have these robo algorithms that tell us what to buy and what not, and economics to identify the microeconomics factor. In the healthcare now, they are using I think in China, in some other places, the artificial intelligence to tell if the patients have COVID-19 or no, or where did they go, so they can track so they can warn the people about whether they met someone that has the infection or no. and many other things for sure to predict whether the patient could be diabetic or no. So they can make some preventive measures. If he is subject to be a diabetic person, then we try to change his health and his diet before the risk occurs. And we have in sustainability as well, where we're trying to, for example, to maintain the infrastructure of the roads by predicting if the infrastructure is wearable, or should it require some maintenance or no, and the number of cars that walk on the roads, is it too much? These kind of questions are answered by machine learning, by modeling the features. And then when modeling the features, we come to understand whether the event will happen or not. You can think about earthquakes, you can think about rains, desert storms, and these kind of things. So we have basically now in every industry, in every field, we have an application for machine learning. And by the way, I don't consider the virtual assistant a machine. It's a machine learning, but because all what we see is virtual assistants, but it's a very small use of machine learning and artificial intelligence, while we have huge, wide applications that we can take advantage of. This is the application I was telling you about. I take the data from the retailers, and then I calculate the safety stock, the demand lead time, and how much to order, and then I give this to the procurement or the purchase department to take actions of what to buy and what not to buy. Of course, I take into consideration the footfall and the popularity of the products and the slow-moving items and items that bring revenue and drive margin and this kind of things. And after, you can convert your algorithm or your model or your machine learning model into an application that can be seen with the business users if they want. You can make visualizations, you can make dashboard for actions, and you can send your modeling work in machine learning to stakeholders to take it further. So it's very easy now in R and Python to do this as well. Python has Dash, R has Shiny, so the field is continuously evolving and continuously updating, and the bridges are being connected now.
Hey, Haytham, let me, we've reached Q&A anyway, but I'm just going to dive in. We had a question raised on the Q&A panel. I'll just read it out specifically. I think you touched upon this, but the question raised is, when would you best decide to use classification, and when would you use regression?
That's a very good question. So thank you, Steve. So in classification, we use it when our target, what we want to predict is limited, is very limited. 4, 5, 6 options you have. So for example, in the example of the New York and San Francisco, how many options did we have? We only had New York and San Francisco. We can have 6 more, 10 more, right? 11, 12, 15 more. But if you have, for example, if you want to model the speed of a car, to predict the speed of a car, or the gallons the car take to walk a mile, this is not categorical, right? This is not options. This is a continuous number you will have. You can have 1.4 gallon, 1.2 gallon, 1.3 gallon. So this is a continuous feature. So if what you want to predict is limited, and you can see the limitations, you can see the options that you have, then it's a classification problem. If your target is not limited, you can have numbers from 0 to 1 million, then it is a regression problem.
Thank you. Thanks, Nathan.
Okay. Welcome, Steve.
Just a reminder, we're moving on to Q&A, but and I'll unmute the session for you all to have an opportunity to speak directly. But if you prefer to type your question, feel free to use the Q&A function.
Yeah.
We had another question come through, yes. Haytham. Sorry. So
please, yes.
In terms of, could you give a real example of a clustering algorithm? Maybe something from your experience, perhaps?
Yes, for sure. So as I told you, the customers, when they buy from, let's say, a certain brand, you have these type of customers. You have a customer that when he goes to the shop, he buys large quantity. When it comes to this shop, I'm like this, by the way. When I buy clothes, I buy once a year from my favorite shop, a big volume, right? And you have the customers that go to the shop very frequently, basically every week, and to buy a small item. So we call this, so we can call this the value shopper, you can call this the loyal shopper. And you have these customers that that like to buy the most expensive stuff, the exclusive stuff, when they just are released in the market. So we can use the clustering algorithm to cluster those kind of customers. So for example, when I cluster the customers that are loyal, I continue to offer them incentives to buy from me, for example. A new customer that's just coming and he only bought from me once and recently, I can have them in a segment, in a cluster. And when I have them in a cluster, I will offer them incentive to continue to buy from me again. So the RFM analysis using Kmeans, recency, frequency, and monetary value is a very popular use of the clustering algorithm.
Thank you. Good example. Thanks, Haytham.
Thank you.
One final question that's come through, and then I'll open the microphones up. Is how to be sure that we are not biased when selecting the options we have, or we should be selecting all the options available?
Very nice. So we have to do some modeling. It's a very good question. We have to do some modeling because you might have like 30 or 40 features in your training data. So you have to see the feature importance, and you don't have to take all of them because you have some features that has no importance to your target. The information you gain from these features is minimal. And when you have this kind of features, you want to try to eliminate them from your model to make your model more robust and less variance when he sees the future. So there is this kind of a sweet. You don't want to take everything, and you don't want to leave everything. You want to take the most important features that really tells that predicts the why, the thing that you want to predict. Like we have seen in the machine learning example, the height, I cannot leave this out of my model, right? Because the model, I don't think it will work without the height. It's a clear distinction between New York and San Francisco, but I can leave something that has no value whatsoever or classified only one observation. So I will not crap my model or crowd my model with this feature that will provide minimal significance to my testing or to my deployment. So you want to be in the middle. That's the feature importance, and only take the features that are very important to predicting your why or your target.
Thank you, Haytham. Great. Well, thank you for those that asked those questions. We've got some time left, so
I can do the demo if they want. I can do the demo in Orange just quickly.
Sure. Yeah, quick demo. I think that'll be very useful. Hopefully, everyone else will find that useful. And I'll begin to open up the microphone. So if anyone has got any questions as you walk through that, feel free to fire away. We have some time to answer some more questions.
Perfect. Okay. So guys, you can download this from Google. It's called Orange for data mining. It's free. You can go to Google and download this. This is a widget-based machine learning studio. So widget-based means there's no coding required. And it is all usually very useful when you start learning about machine learning because it's easy to visualize the data when you need. So let's take some data. So as you see, everything is run by widgets. I have this banking data set where the job of the person and the marital status, the education of the person, and so on, and the outcome I'm trying to predict whether this person subscribed to the service of the bank or no, based on many features as the duration, the duration of the calls, the loan, and these kind of things. So we have features, those are our axis, and we have Y, this is our target. And we can use the visualized widget to make some simple visualizations of the data. So you can, like we did for the decision tree, we can see, like, for example, which months the call happened or the contact of the customer happened. And we can see the how many people said yes to the subscription, how many people said no to our subscriptions, and you can come to understand the different features that you have, how many blue collar you have, how many management you have, and so on. Very useful to visualize before you model. And then you have here the modeling window. And you want to take, for example, let's take two models. Let's take the decision tree that we have seen, and let's take logistic regression. And if you know now, the target was yes and no, right? So this is a classification problem. I have two options only. And let's take the logistic regression. You simply connect the data with the tree. How did they know that Y is the yes or no? Because in this file, I have set that the target, if you remember, I said that I changed this to be the target. I have specified beforehand what is my target, right? So when I connect the widgets together, it knows that it's trying to predict Y. I'm facing some slowness. Okay, and then we can test and score. And we can also visualize the tree, I think, to see there is a tree viewer. We have 40,000 rows, and that's why maybe the data is. So this is similar to the tree that we have seen in the San Francisco and New York example. And you can see how easy it is to model a decision tree using this widget based. So I'm saying here, if the duration is less than 410, so most probably it's a no. If the duration is more than 410, then most probably, well, we have to see about it. Not most probably it says, but we have to still see about it. And this is 4 level only. And you can see that the tree can go up to down many levels. So we can further make the tree more complicated. And then you can evaluate between both models. So let's evaluate between the tree, decision tree, one model of machine learning. If I can connect the dot. And the logistic regression. And we connect the data also to it. So it will start testing and scoring. And what it will do now is it will create the test and train by itself. Because if you notice, we did not split the data, like we said in the presentation. The test and score, it actually splits the data for us to train and test it. And it also makes something called cross-validation, where it takes several test samples and continuously or iteratively test on these many test samples. Kind of a more confirmation that our model is good. I'm doing the test and score to see which model will provide the best accuracy and the one I can use for the future. So let's see the results. So it seems that the logistic regression have better area under the curve and have better precision and recall. And in general, it has also better accuracy. So this is classification accuracy. So now, if I bring another data, and this will be the test data has to be exactly like the training data, same column names and same everything, or else the model will not work. So this is my test file. And let's create some predictions. So to create predictions, I connect the unseen data with predictions. And I connect, let's connect the logistic regression with predictions. And you can see here the results. So here, this is the actual observation. So for example, here was yes, the logistic regression said no. Here was yes, the logistic regression said no. Here was yes, the logistic regression said yes. And you can notice when we have seen the visualization that I have one Q&A, okay, just 1 second. We can notice when we have seen the observation that we have very limited number of yes and many numbers of no. Yes, please, for the Q&A.
I think we've just had a couple of questions that come through the chat asking the name of this this piece of software is Orange. Is that correct?
Yes, Orange for data mining. It's a free open source, and you can use it to do clustering, classification, and it's very good as a starter for your machine learning journey. Just go to Google, write Orange for data mining, and then download the open source version.
Brilliant, thank you.
Hello.
Thank you, Steve.
Yes, hi, is that Omar?
Yeah, it's me. Okay, my question is that when are we supposed to stop? For example, when we are doing testing on data which is set by us, right? And we are not biased, and we have set the balance between the biasness and the variance, and we get a good amount of percentage which we are satisfied. But when we run the data in the real time, what is the percentage that we should be comfortable that when are we supposed to know that, okay, now this application or software is working properly?
That's a very beautiful question, and you don't have a standard for this. I'll tell you why. First of all, you need to compare between different models, and then you select the model that has the highest accuracy on the test data, not on the training data. So this is number one. This is like a rule of thumb, to select the best model that have the best accuracy on the test data. But I've faced this before. I do a forecasting model or a machine learning model, and the best accuracy I get is 70%. I cannot be more than that. I just can't. I tried everything, I can't. So the question here is different. Shall you continue with your model, or shall you scrap the whole project? So it's a kind of management decision, you know. Rule of thumb, if your accuracy is more than 90% on the testing, then your model is very good. You can work safely and use this model and deploy this model in real time and production.
And I guess just to add, Haytham, we would guess on the criticality of the business problem you're trying to solve.
For sure.
I guess in healthcare, you might want to be as accurate as possible, whereas
perfect.
Perhaps in retail marketing, then you can live with a slightly lower list of accuracy.
Brilliant remark, yes.
Another question that's just come in terms of the questions of the file that you use, the source data, how is that organized? Is there any particular rules that people should consider when organizing the source data?
You mean the structure of the data? Yes, you want to remove DNAs, non-available. You want to make the data, if it's a number, it should be a number, because sometimes, you know, Excel, for example, has the numbers, the thousands have comma. When you import this in R or Python, R and Python doesn't understand the comma of the thousands, so it treats it as, so you have to convert and transform the data to be numeric. You want to remove the outliers as much as possible. So outliers means that, for example, the average height of people, all of us, are between, I will talk in meters because I don't understand feet, between, for example, 1.65 to 1.85. But we do have these very tall people and the very short people, right? So we want to remove the outliers to make your model more robust, to remove the the anomalies in the data before modeling as well. We call them the inliers. Keep only the inliers and remove the outliers.
Great, thank you.
Haitham, may I ask
Yes,
a question? All right.
Yes, please.
What I was trying to know, in this tool Orange, you use that input file. For example,
Yes.
I have an Excel file with some columns, maybe like name, like you shown the profession. It could be a housemaid or engineer or doctor, etc. So if I use such an Excel file or maybe a Word, Microsoft Word with a table, would it help the Orange can analyze the data and show me the results like this?
I think it's better that you arrange it in a CSV or an Excel file, and then it can help you visualize the data and arrange it and do a lot of modeling with Orange. Orange has one disadvantage for sure, is that the models are limited and the scale of the data will not be complete. Python and R. With Python and R, I can do 3 million rows at one go. Here you can't, but this is very beautiful and easy. If you have a simple problem, 10,000 rows, 20,000 rows, you want to model and gain some information from.
Thank you, Haitham.
Welcome.
Great, thank you. I think that answers the majority of the questions. If you do have any further thoughts or questions or items you want to explore a little bit more, then feel free to contact us after today. We'll distribute the recording of the session, so then you can get back in touch with us if you wish to. The last thing, just in terms of a wrap up here, just to say thanks everyone for their participation. Haitham, I don't know whether you could bring up the final slide. Thank you very much.
1 second. Yes.
Just to mention, we are running a micro-learning session, so if you wanted to explore some of the principles and concepts that Haitham's covered today for yourself in practice, then we are running a short 4-hour micro-learning session specifically on some of the methods that were covered today, so you can try this for yourself. We're running that as a remote live session with Haitham on the 16th of July. And for those that have attended today, we're offering a 10% discount to attend that course, priced at $100 US or local currency equivalent. So if that's something you're interested in attending, please do get in touch. We'll get you booked onto that session. And the last thing for us to say, we hope you found this session useful. If you did, then please do follow us on LinkedIn. Please do subscribe to our newsletter. All of the information will be provided to you via email in the next 24 hours. Thank you very much, Haitham. Hope you all found that enjoyable, and have a good day ahead, everyone.
Thank you.